And into every nice concept, a few numbers must fall. So we're going to take a look on our dear friend, the glass, at a couple of the numbers and some of the calculations involved in thinking about magnetic nuclei and the relationships between frequencies, magnetogyric ratios, strength of magnetic fields, spin states, and all the other fun stuff. So, to follow up on what we've talked about before, there's a critical number that I want to make mention of again, and that is this, the spin quantum number. And the key idea behind it is it tells us the number of unpaired spins that generate a magnetic field in a nucleus, but it also tells us how many states that nucleus can adopt in an external magnetic field. The equation for that, it's a pretty simple little relationship, is 2I plus 1. And what that tells us is, again, the number of states a nucleus can adopt in an external magnetic field. Taking as an example for just a moment, for either the proton or the carbon-13 nucleus, two of the most common that we look at in NMR spectroscopy. If you recall, these are both spin 1/2 nuclei. And if I plug that in to this little relationship here, I come out with a 2. And that simply tells me that whenever a proton or a carbon-13 nucleus is put into the big honkin magnetic field, then it can adopt 2 different spin states, and only 2. Out here in the environment, they can be oriented with their north poles pointing in all possible directions. In the external magnetic field, they can be aligned only in one of 2 ways, either north pole to south pole or north pole to north pole. There are no other options available for a spin 1/2 nucleus like this. Now we've drawn pictures kind of to try to reflect that, and this is a fairly simplistic one here, where we draw this. I'm going to label it B0, our representation for the big honkin magnetic field. And then we represent the 2 spin states a proton or a C13 or any spin 1/2 nucleus can adopt this way. We'll just simply draw 2 little energy levels, okay? And there'll be a difference in energy between these. Change in energy is simply h nu, one of the most fundamental equations of spectroscopy. And we will depict the low energy configuration this way. North pole of the magnetic nucleus pointing to the south pole of the big honkin magnetic field. But there is one other way that that is legally arranged. It is higher in energy, north pole to north pole, south pole to south pole, with a difference in energy between them. And the bulk, or the main point about NMR spectroscopy, like with all forms of spectroscopy, what we use is photons to transition between these 2 states. Now, of course, there are other nuclei. The deuterium nucleus, heavy hydrogen, hydrogen 2. 1 proton, 1 neutron in the nucleus of this one. If you recall, this one has a spin quantum number of 1. 1/2 for the unpaired proton, 1/2 for the unpaired neutron. Together they make a spin quantum number of 1. If we calculate how many spin states this one can adopt in an external magnetic field, the calculation is pretty simple, as they tend to be here. It comes out 3. And I interpret that as saying when I drop a deuterium into our big honkin magnetic field, and again I'll reproduce it this way, a deuterium, a heavy hydrogen nucleus, can adopt 1 or 2 or 3 possible orientations. Okay, it's a little bit harder to depict these than it is for a spin 1/2 nucleus. Is it, north pole, south pole, north pole, and what's the third one? Up, down, sideways? It's a little bit difficult to visualize, but I can tell you for sure that this nucleus adopts 3 possible spin states, each of them separated by a certain amount of energy. Okay, the same amount of energy here. There are even more complex nuclei. One of the more interesting ones is cobalt-59. This one, it turns out, has a spin 7 halves. 7 unpaired spins in this nucleus, meaning if you punch it out on this calculation here, 7 halves plus 1 equals 8. A cobalt-59 nucleus in the big honkin magnetic field takes on 8 possible spin states. This is what I mean when I say the quadrupolar nuclei, the nuclei with spin quantum numbers greater than 1, generate magnetism just like the simpler nuclei, but the magnetism is considerably more complex, with a greater number of spin states, 3 for deuterium, 8 for cobalt-59. The transitions between them just become much more complex. And this is one of the principal reasons why in NMR spectroscopy we tend to focus more often on the spin 1/2 nuclei, simply because the magnetism is much simpler to think about, to model, to diagram, and interpret when we use the spectra to get information about our molecular structures. I left this little part of our diagram after applying the magic eraser. So I want to take a look at this and talk a little bit more about just this picture for a moment. Because interestingly enough, this one aspect of NMR that's different from other forms of spectroscopy is the presence of the external magnetic field. The separation in energy that we see when we put, say, a proton or any spin 1/2 nuclei in the big magnetic field and then start probing how much energy does it take to turn it over, to move it to the other spin state and add a little bit of energy to it. When we do that, a lot of that is controlled by how big a magnet do we have, okay? How big of an external magnetic field do we actually have? For example, if we have a different NMR spectrometer and that has a larger magnet, and there are certainly instruments like that out there, I'm going to kind of diagram it this way, okay? Just trying to be almost cartoon-like and exaggerating it here, that this is going to be B naught. If this was the big honkin magnetic field, this is the really big honkin magnetic field, a much more powerful magnet than this situation. Our proton, when we put it in the super magnetic field, is going to adopt 2 spin states, just like before. That hasn't changed. But what does change is this. The energy separation between those 2 spin states. That changes. Okay, meaning the frequency of the photons necessary to reach in and grab this nucleus and change its magnetic orientation is different now. And as we will talk about later, there are actually a number of significant advantages to using a more powerful magnetic field to get the energy separation between the spin states of the nuclei we're trying to study as far apart as we can possibly get them. And so one of the main driving forces in NMR spectroscopy since its inception is to study it and build instruments with ever increasingly powerful magnetic fields. And of course, the one limiting factor on that process is simply this. The larger the magnetic field that you need, the more it's going to cost. So that is always, you want as big a magnetic field as possible, but there are, of course, limits as to, how much of a magnetic field you can actually work with or actually, get a hold of. Okay? It always comes down to money, generally. All right, once more with a magic eraser, and then the actual calculations. Now, we've seen this equation. I'll rewrite it up here. The standard, most basic equation for spectroscopy. But I do want to add now another aspect to this thing, and that is there are 2 factors that control the size of the energy gap between our spin states for proton or carbon-13 in our, in any magnetic, any NMR instrument. And that is, one of them, the size of the magnetic field, B naught. How much did you actually purchase? That one is controlled by us. It's the funding level. But there's a second aspect to it. Each and every nucleus magnetic nucleus, proton, carbon-13, or some of the others, they may act like magnets, but some of them are more powerful magnets than others. Nature gives them their own inherent characteristic magnetism. And so that one is symbolized. It's called the magnetogyric ratio. And there's a separate value for proton, for C13, for fluorine-19, phosphorus-31. There's even a magnetogyric ratio in principle for carbon-12. For that nucleus, it's 0. It is not a magnetic nucleus, but you can assign a magnetogyric ratio to it. And so this takes into account the fact that there are actually two factors, one nature controls, one we control, that tell us what frequencies of energy we are going to need in order to transition nuclei between these two spin states. There's a couple other aspects to this equation, and no surprise here. Okay? Planck's constant, like any self-respecting chemical or a physical equation, Planck's constant plays a role. And as a bonus on this one, we even have over 2 pi. Oh, it's a beautiful little equation here. And if you look at it carefully, you'll notice the way I've written it here, Planck's constant appears twice. It can be easily canceled. And that gives us this. And this is probably the most fundamental equation in all of NMR spectroscopy. It's called the Larmor equation. And it basically tells us for whatever combination of nucleus and magnetic field that we want to use, here are the frequencies you need to generate, the frequencies of light you need to generate in order to get nuclei to transition between their various spin states in the external magnetic field. So a couple of the numbers that we are working with here. One, the magnetic field. On the instrument we own here at Georgia Southern, okay, we have what is referred to as a 9.39 Tesla magnet, okay? Tesla standard unit for measuring strength of magnetic field, okay? That's the magnet we have, and that's a powerful magnetic field. NMR uses stronger magnetic fields than almost any other application of magnetism in all of science. The other number we need is the magnetogyric ratio of proton, okay, for good old hydrogen atoms. And the number, and I'll just simply write it out here, there we go, 267.512 times 10 to the 6th. And the units are a little bit odd, but you'll see how it works out in just a second. Radians per Tesla second. These are the two critical numbers we need. This one, supplied by nature. If you look up, magnetogyric ratios for nuclei, you might see different values. It all depends upon what units they're being reported in. But it's all the same number. It's just maybe the units attached can change. I like using this one here. This is the one supplied by nature. This is the one, this number, the external magnetic field, is the one we bought. So if I plug them in, the Larmor equation, what I'm going to get is, okay, what is the frequency of light I need to make a proton transition between its spin states in our magnetic field? And so if I start plugging away, 267.512 times 10 to the 6th radians per Tesla seconds. Oh, that looks good. Times 9.39 Tesla. Oh man, divided by. And now that's over 2 pi. And remember, 2 pi is pretty much the definition in mathematics of a radian. Okay, 2 pi radians. So that means my radians cancel, Tesla units cancel. The only units that I have left are reciprocal seconds, okay, which I'm calculating a frequency. Kind of nice it worked out that way. And the number I got when I punched this out on my calculator, 399,787,298 hertz. Okay? That is a big, cumbersome looking number. And that is why you will often see it always written out simply 400 megahertz. Okay? And when you look at the instrument, that's the number you're going to see printed on the magnet itself. And that's why we say, you know, at Georgia Southern, we have a 400 megahertz NMR spectrometer. That is the frequency of light we need to make protons transition between their two spin states in our magnetic field. Okay? As far as instruments are concerned, it is not the smallest one available. It is not the largest one by any shot available. It is a nice mid-range instrument. It does pretty much everything we need it to do here. It's a good standard standard type instrument that does a lot of interesting stuff for us. So there are the calculations involved in the relationships between frequencies, magnetic fields, magnetogyric ratios. So take that into account, study that over a little bit. You'll have the opportunity to practice these, and we'll see you later.